Bismillahirrahmanirrahim. Welcome everybody to this video, which is about atomic species balances around reactors. So in this video, I will show you how I apply the atomic species balances around reactors by solving two examples. One is regarding a single reaction problem, and the second one is regarding a multiple reactions problem. Before we start, I want to remind you that there are three methods of applying material balances around reactors, which are the extent of reaction, zeta, or by using the molecular species balances, or by using the atomic species balances. I will show you how I apply the third one, the atomic species balances. If you remember, the general material balance equation is that accumulation is equal to the summation of input and generation minus the summation of output and consumption. And in the third method, we are talking about atomic. So in atoms, we don't have accumulation. We have neither generation nor consumption. So the material balance equation will be reduced to input is equal to the output. And all of our calculations will be based on this fact. There are advantages and disadvantages of applying the atomic species balances by my way. The advantages are that it is much faster than the ordinary way of applying the atomic species balances, and also it is more organized. The disadvantage is that it has some calculations details, so it is like under the hood, if you can say. There are 10 steps. Here are the steps 1 to step 5. I will not go through them. You can pause the video to read them or to print them, because I will go through them one by one during solving the examples. I think it will be much easier if I solve the example, then you can go to read to understand them. Maybe now it will not be very clear to you, but here are the first steps. And here are step number 6 to step number 10. We have 10 steps. There are short, actually. I just make them 10 steps so they will be clear for you, but maybe all of them will not consume much time, so don't worry about the number. So this is the first example, which is regarding a single reaction problem, and the steps number 0, or the 0th step, of course, is to read the question. So here the question said that acrylonitrile is produced in the reaction of propylene, ammonia, and oxygen. So this is the acrylonitrile produced by reaction of propylene and ammonia and oxygen. It said that the feed contains 10% mole propylene, 12 ammonia, and 78 air, not oxygen, it is air. A fractional conversion of 30% of the limiting reactant is achieved, taking 100 mole of feed as a basis. Determine which reactant is limiting. So he wants us to determine what is the limiting reactant, and also the percentage by which each of the other reactants in excess, and the molar amounts of all product gas constituents for a 30% conversion of the limiting reactant. So he gave us the conversion of the limiting reactant, but he didn't specify which one of the reactant is the limiting reactant. He wants us to determine that, and also wants us to determine the molar amounts of all the product gases. So let's go to the solution. So the first step is to balance the chemical equation. Usually it is given balanced already, but we have to make sure that it is balanced. So here we have 3 carbon, that set of carbon, and also here we have 3 carbon atoms, so carbon is balanced. hydrogen, we have here we have 6 and 3, this is 9. Here we have 3 and 6, also 9. So hydrogen is balanced. Nitrogen, here we have just 1 and here we have just 1. This is also balanced. Oxygen atoms, we have here 3, 1.5 multiplied by 2, and here we have 3. So the equation is balanced. So our first step has been finished. The second step is to label each molecular species by a different letter without repetition. These are the molecular species. So just give each one a unique letter. So this is for the propylene, we put the letter A. For the ammonia, B. Oxygen, C. Acrylonitrile, D. And water, E. Okay, we have already finished 2 steps out of the 10. So it is easy, as I told you earlier. Now the third step is to construct a table where a row for each label from the previous step, the molecular species, and inert if there is any. It should be the first one. So here are the molecular species. We labeled them. We just put them in a column. And inert, if we have, and put it first one. We have inert because the reaction is just for oxygen, but we have air. So the remaining of the air, we will specify it as inert. The second thing is a column for each atomic species. We have here which atomic species. We have from here the carbon and hydrogen. Here we have nitrogen. Hydrogen already we put it. And here we have oxygen. We can just be enough with side of the reaction, either the reactant or the product. Or if you want to make sure, just go to both sides. So here carbon already there, hydrogen already there, nitrogen already there, hydrogen already there, oxygen already there. So we are good. So for the fourth step, it is basically that for each of the feed molecular species, the reactants and inert add subscript n. So here are all the molecular species, but we just want to add for the feed, the reactants ABC and the inert. So we add subscript n. Then add a new row for each one of the feed again with subscript out. So what we put in as a subscript, we'll add a new row for each one of them with subscript out. The next step is to make a bold solid line after the last species within subscript. So this is species, not the last one. Okay, so after C we have nothing with subscript in. We will add a solid bold line. Why is that? Because if you remember the general material balance equation, it was reduced to input is equal to output. So this is like the boundary line. Okay, the next step is to plug in how many atoms in each of the atomic species in each of the molecular species. So first of all, the inert, make them empty. For the A or the C3H6, just put 3 hydrogen and 6 carbon. Forget about any number on the equation because it will be the same. But as I said earlier, we hide some calculations details, so just put them without looking at the stoichiometric coefficients. For the NH3, we have 1 nitrogen and 3 hydrogen. For the oxygen gas, we have 2 oxygen atoms and you can say that we put them in the in and out with the same number of atoms, which is logical, of course. Then for the acrylonitrile, we have 3 carbon atoms, 3 hydrogen atoms, 1 nitrogen, and for water we have 2 hydrogen and 1 oxygen atom. The next step is to plug in a new column the given moles or flow rates and use all the given additional information. So we'll add a new column for the moles. It is given that we have 100 mole as basis and 10 of it is a propylene. 10% of 100 is 10. Also propylene is a 12, but we don't have oxygen directly, we have air. So we need to use that information that the number of moles of oxygen gas is equal to the total number of moles of air multiply the mole fraction of oxygen in air, which is 0.21, and the moles of air is 78. So the number of moles of oxygen is 16.38 mole. We plug it in, and the inert now we can know it because we know the air and we take off some of its moles for the oxygen gas. So also the moles of the inert we can know, and it is 61.62. And because it is inert, its input is equal to its output, even as molecular species, because it is non-reactive. Yet we didn't use all given information because we were given the conversion of the limiting reacting. But first, to use this information, we need to determine which reactant is limiting, and here it is, determine which reactant is limiting. And here we need to use the balanced equation and its stoichiometric coefficient. So A and B, we have 1 to 1. However, we have 10 moles, the actual moles we have 10 of A and 12 of B. So A is the limiting because 1 to 1, so we should have 10 to 10, not 10 to 12. Now let's compare A and C. Now we know that A is limiting if we compare it with B, but let's compare it with C. We have in the balanced equation 1 to 1.5, which is a 3 over 2. However, the actual moles for A we have 10, but for C we have just 16.38. We should have 1 to 1.5. We have 1 to 1.5, so we should have 10 to 15. But we have 16.38, so A is limiting. Now part of the question is to determine the percentage by which each of the other reactants is in excess. For B, we need just 10, but we have the actual 12, so the axis is 20%. And for C, we have 16.38, but according to 1 to 1.5, we should have just 15. So this is the excess percentage of oxygen. The actual minus what we should have, divide by what should we have, or what's just enough if there is no excess. Since we determine the limiting reactant and we have the conversion, we can now calculate the unreacted moles of that reactant, which is A. So the remaining moles of A is 1 minus the conversion, because 30% of the input moles of A has been reacted. However, the remaining, this is why minus 1 minus the conversion, its complement is the unreacted. So it is basic math, and we will have 7 moles of A that is not reacted, that we have it as an output. We use all the given information and the moles. Now we can calculate the degree of freedom to know if we are able to solve the problem or not. To be able, the degree of freedom should be equal to 0. If you do my method, the degree of freedom is basically number of unknowns minus number of atomic species. The number of unknowns, we have 4 unknowns remaining after using all the given information, and we have 4 atomic species: carbon, hydrogen, nitrogen, and oxygen. So 4 minus 4, the degree of freedom is 0, and this means we can solve this problem. Now let us do the 9th step, which is do atomic balance by choosing an atomic species with the least number of unknown moles or flow rates. So for carbon, we have here, we know its moles, here we don't know, here we know. So just one we don't know, so we can start with it. But for example, if we start with oxygen, here we know, but here we don't know, and here we don't know. So there are 2 unknowns on the oxygen balance, so we don't start with it. And nitrogen, here we know, here we don't know, here we don't know. So also we will not start with the nitrogen. For the hydrogen, we know here also it is known, here it is unknown, here also it is unknown. So we don't have any other choice other than start with the carbon balance. If we use the carbon balance, basically 3 multiplied by its moles, 10. Then we go through the solid line, so we'll put equal, because this is input and here is the output. So equal, here 3, we don't know unknown, d, plus 3 multiplied by 7, and it is easy. Linear equation with one unknown can be solved easily. Okay, now we plug for D we plug 3, and now if we go to the nitrogen, this is known, this is known, this is the only unknown. We have just one unknown, so we can do the nitrogen balance. It is 1 multiplied by 12. We come to the bold solid line, so we will put equal, then 1 multiply 3 plus 1 multiply B out, so B out is 9. We plug it in and we continue doing the balance, and we will fill in all the moles. So now all the moles are known after doing the atomic species balances. We can also go further to calculate the mole fractions of the product, or of the output actually. The question here didn't ask for that, but in general we are able to do that. So let's see how. So in the 10th step, it said that for mole fractions, calculate the total number of product moles, or the output, because we have also the inert to consider. Then in a new column, divide each molecular species moles by that total. So here are the outputs, the products and the inert. We will calculate their summation, which is 101.5. Then we will divide each moles of a molecular species by that total, and the total should be 1, and you can calculate it as a fraction if you want. So let's go to the second example, which is regarding a multiple reactions problem. Yield and selectivity in a dehydrogenation reactor. The reactions ethane will give us ethylene and hydrogen gas, and also ethane and hydrogen gas will give us methane. Take place in continuous reactor at steady state. The feed contains 85% mole of ethene and the balance inerts. The fractional conversion of ethane is 0.501 and the fractional yield of ethylene is 0.471. Calculate the molar composition or molar fraction of the product gas and the selectivity of ethylene to methane production. So this is the 0th step, is to read the question. Now the first step was to balance the equation. So let us make sure that both equations are balanced. Here we have 2 carbon atoms and here 2 carbon atoms, so we are good. Here we have 6 hydrogen atoms and we have 4 plus 2, which is also 6. So the first equation is balanced. The second one, here we have 2 carbon atoms and also here we have 2 and 8 hydrogen atoms, and here we have 8 hydrogen atoms. So both equations are balanced. The second thing, or the second step, if you remember, is to put the unique letter for each molecular species. So for ethane we put A, for ethylene we put B, for hydrogen we put C. Here we don't put again because it is already, there is a letter for the ethane and also for hydrogen. For methane we put letter D because it was not in the first reaction. Now we put or construct our table for the inert, or for feed, the inert and the reactant. We will put subscript in and we add them and subscript out, and we have just 2 atomic species, carbon and hydrogen. If you can see, they are repeated again and again. Then we plug in, like for each atomic species, how many atoms in each of the molecular species. Here we have 2 carbon and 6 hydrogen atoms. We will repeat it in the out as well. For the ethylene 2 and 4. For hydrogen gas we have 2 hydrogen atoms, and for methane 1 carbon and 4 hydrogen. For ethane we already specified that. And remember to ignore any number after balancing the equation. Just deal with them as the coefficient is 1 before all of them. Now let's use the given moles and given information. So the feed contains 85% moles of ethane. If we specify basis of 100 mole, it will be for the ethane it is 85, and for the inerts it's 15. It gives us the fractional conversion of ethane. Here it is. So this number is used to produce the product, so the rest of it, or the complement, 1 minus that number of the input of ethane will give us its output. For the yield, I don't know if you remember the formula for the yield, but basically it is the actual moles divided by the moles that we will get if we don't have side reaction and if the limiting reactant has been consumed completely. So if we don't have this reaction, if we just have this reaction, and if the ethane consumed completely, so it is 1:1, and for C2H6 or ethane we have 85, so we should get 85, but we have side reaction and it is not fully converged of ethane, so it is 1:1, and the yield is equal to the B divided by the AN, and if we multiply them we will get 40. So instead of getting 85, because we have other reaction and the ethane didn't completely converge, we get just 0.471 out of the 85, which is 40.035. Okay, now the degree of freedom. If you remember, after using and plugging all given information and moles, we have two unknowns, the mole of hydrogen gas and the moles of methane, and we have two atomic species which are carbon and hydrogen, so degree of freedom is 0, so the question can be solved. Now we are ready to perform the atomic balances. We have carbon and hydrogen. How to decide which one to start with? For hydrogen, here it is known, here it is known, here it is unknown, here it is unknown. So we have two unknowns. For carbon, here it is known, here it is known, here it is unknown, and here it is known. So just one unknown. So we'll start by the carbon balance. 2 multiplied by 85 equal, because we reach the boundary line of input and output, equal to multiply 40 plus 1 d plus 2 multiplied by 42, we get d. So now we have just one unknown for the hydrogen, so it can be also solved. We have now all the information about the moles of the feed and the products. The question asks for calculating the molar composition, so we need to do a further step. First, we calculate the total of the product, and don't forget the inert. This is the total. To calculate the fraction, we will just divide each mole of the molecular species by the total, and by this easy method or this table we organize everything. So here are the molar compositions of the product and the inert. The second part of the question asks for calculating the selectivity of ethylene to methane, the desired product, the mole of the desired product over the moles of the undesired product. We have 40.035 over 4.1, and we get 7.85 moles of the desired product for every mole of the undesired product. Here is a practice question. Please try it by using this method, and write the answer in the comments on YouTube or Twitter or anywhere, or ask me directly so I can tell you whether it's correct or not. And it is example of the book. You will see the name of the book in one of the examples slides. We reached the end of today's video. I hope it was useful and enjoyable at the same time. See you in other videos, and thank you for listening.